In the previous lecture, we have learned about the term entropy. Entropy. Yes. What is entropy? In the previous lecture, we have defined entropy, the quantity Q by T or dQ by T remains unchanged in an irreversible process and is called the entropy of the system. So in an irreversible cyclic process, change in entropy Q by T or dQ by T remains unchanged. One more thing we have learned, the entropy is path independent. Now we are coming to Clausius inequality. Clausius inequality. Suppose this is a cyclic process A, K, B, H. Okay. We are dividing this cyclic process into small quasi-static process A, B, C, D, E, F. So AKPHA is a cyclic process and which passes through a set of states represented by small states A, B, BC, CD, DE, EA. Through these small steps, it is going from AKPH A. And AB process temperature is T1, this is temperature T2, this is temperature T3, this is temperature T4, and so on. Now, here we consider A, B, C, D. This is, let me draw first. A, B, C, D, E, C1, C2, C3, C4, and this is kept at the temperature T0. This is the same A, K, B, H, A cyclic process. We consider a number of Carnot engines C1, C2, C3, C4 working between the reservoirs at temperature T0 and by T0 is greater than T1, T2, T3, ... So this is the cyclic process, reversible process. This is AKPHA, which is following by small states A, B, B, C, D, E, F. Now here we are running Carnot cycle C1, C2, C3, C4, which are connected to a hot reservoir at T0, and A, B, B, C, C, D, D, E are kept at the isotherms at T1, T2, T3, T4 by T0 greater than T1, T2, T3. Now, let Q10, Q20, Q30 are the heat extracted from the reservoirs at T0, and Q1, Q2, Q3 ... are heat rejections at A, B, B, C, C, D, D, A by the Carnot engine C1, C2, C3, C4. So from the hot reservoir kept at T0, we are extracting the heat Q10, Q20, Q30 by the Carnot engine C1, C2, C3, and rejection of heat at the A, B, B, C, C, D, Q1, Q2, Q3. Now, what is happening here? This is AB kept at T1. This is that means it is the isotherm. Isotherm BC kept at temperature T2. It is kept at temperature T3. But you see, when the heat is rejecting at A, B, B, C, C, D, D, the temperatures are remaining constant in A, B, B, C because they are isotherms. So, if the process continue in like this process way, then total AKPHA, when the process will be completed, there will be no heat gain during the cyclic process, because I am repeating here, AP, the Q10 heat is extracting from hot reservoir, Q1 heat is rejecting at AB process, but temperature remaining constant. So, as the temperature remains constant through the process AKPHA, so the total heat gain in the process is 0 as the temperature remains constant. So, according to Carnot cycle, we know Q10 by T0 equal to Q1 by T1. That means Q10 equal to T0 Q1 by T1. Similarly, Q20 equal to T0 Q2 by T2. So total heat absorbed by the Carnot engine, Q0 equal to T0 summation over Qi by Ti, I equal to 1 to n. And this amount of heat is extracted from the hot reservoir kept at temperature T0. And all of this is converted into work. Because there is no heat gain during the process AKPHA. So this is complete violation of second law of thermodynamics. So Q0 must be less than equal to 0. Because here we see this, if Q0 is T0 Q1 T1, that means greater than 0. This is the heat gained from the hot reservoir T0, then it simply violates the second law of thermodynamics. So Q0 must be less than equal to 0. So what we are getting, T0 summation over Qi by Ti must be less than equal to 0. Therefore, summation over Qi by Ti must be less than equal to 0, I equal to 1 to n. If n tends to large, then summation over dq by t must be less than equal to 0. This is valid for the process AKPHA. This is a cyclic process. This cyclic process may contain reversible path, irreversible path. We have not, this is Carnot cycle is operating between AB and T0 process. This Carnot cycle is completely reversible. But AKPHA is a reversible, a cyclic process. But we have not defined it whether it is a reversible or irreversible. This is called Clausius inequality. This is called Clausius inequality. Now we are dividing this process something like this. A K P H. This is irreversible process, and this PHA is a reversible. So close integration dq dq by t must be less than equal to 0 we get from the process inequality. So we can write ABC dq by t plus AKP dq by t, this is for irreversible process, and dq by t for reversible process, this is PHA must be less than equal to 0. So AKP dq by t irreversible plus S A minus SP must be less than equal to 0, because change in entropy during an reversible process is independent of path. So the entropy here and entropy here, the difference of entropy SA minus SP will give this term PHA, total change in entropy during the process, PHA. So SA minus SP less than equal to 0. So SA minus SP which be greater than equal to dq by t irreversible. So what we are getting, this is the change in entropy during a reversible process. So SA minus SP dq by t irreversible process. From this we are getting this dq by dt during an irreversible process plus SA minus SP equal to 0. So from this we can write SA minus SP dq by t irreversible. So SA SP plus dq by t irreversible. If we consider the process is an isolated process, simply adiabatic process, then if we consider the process is simply adiabatic and isolated, so dq terms vanishes, so SA greater than SP. I am repeating, from this we get SAP SP. If we consider that it is an isolated adiabatic process, so dq term vanishes, so SA greater than SP. So the entropy, final entropy SA is greater than initial system in an irreversible process. So entropy always increases. I am repeating, this is, you see, SA equal to SP plus dq by t irreversible process. So the change in the entropy at the point A, the final point, is always greater than the initial point SP plus dq by t irreversible. If we consider that this is an adiabatic process, this term vanishes, so we get SA greater than SP. So the entropy of a final state is always greater than the initial state during an irreversible process. This is called the increase of entropy. This is the law of